Okay, so let me begin again. So today we have Ehsan Shahoseini from Iran. He will speak on the introduction to the deformation theory of Galois representation, part 1. He will continue today's talk next week also. So over to you, Ehsan.
Thank you. And thank you, Divanja, for encouraging me to give presentations. And yeah, I really didn't know anything about deformation theory, but now I know something because of this presentation. So thank you, him. I'll start with two conventions that all representations are continuous and the group G is a profinite group. Let us pick some notation. Capital K is a number field and little k is a finite field. S is a finite set of primes of a given number field. K bar is a chosen algebraic closure of K, and K bar S is the maximal algebraic extension of K in K bar, which is unramified outside S. So just we have finite set of primes that can be ramified. GK is the absolute Galois group of K, and GKS is the Galois group of K bar S over K, which is the inverse limit of all finite Galois extension, Galois group of all finite Galois extensions that discriminant of L over K is divisible just by primes in S. So this is also again a profinite group. We have this diagram.
Just repeat the last definition.
Yeah.
Yeah, so this is some different Galois group. Or local,
this is not local.
Okay, then what is the
This
role of S?
Ks is the maximal algebraic extension of K, which is unramified outside S, and GKS is its Galois group.
Okay, okay.
For example, algebraic extensions of Q that are unramified outside 2 and 3, for example. We have such a diagram. K bar is an extension of K bar S and an extension of K. We have these Galois groups, and we have local analogs, the completion of K at some place L, and its algebraic closure, and its absolute Galois group I write simply instead of GKL by GL. And here we have a choice of embedding. Note that this group GL is also profinite. And this embedding is, in some sense, someone said that not important, but really it is important because we have these maps, because GL is really the decomposition group, so it's a subgroup of GK. But I write not an exact arrow. This is dot arrows, these two arrows, and with this surjection, we get this commutative diagram. So we get this map. This is dotted arrow also. And the point is that these dotted arrows, especially this, depends on the choice of this embedding. So it is well-defined continuous map just up to conjugation, not an exact map. This is well-defined just up to conjugation. Let me make 2 remarks, or 3 remarks. First, kernel of this surjective map is the closed normal subgroup generated by all inertia subgroups of GK attached to places L not in S. So really, it is a very big kernel. It has a very big kernel. Second one is that GL, the local Galois group, is topologically finitely generated. Thus, GK is topologically countably infinitely generated because first, GK does not cover by a finite number of GLs, but it covers by an countably infinite number of GLs. So it is topologically countably infinitely generated. And the third remark is that we don't know about topologically finite generation of GKS. Note that S was finite set of primes. This is a conjecture if I say truly due to Shafarevich that it is finite, topologically finitely generated, but it is an open problem, not so. For fixing this problem, that is not, this is not known to be topologically finitely generated, we impose a weaker finiteness condition than finite generation. Definition is as follows. Let P be a prime number and G be a finite group. We say that G satisfies P finiteness condition if for all open subgroups G naught of G of finite index, we have the set of continuous homomorphisms from G naught to Z mod PZ be finite. And GL and GKS satisfy P finiteness condition for all P. For GL, it follows from its finite generation. Finite generation is really P finiteness condition is a weaker condition than finite generation. And for this, it follows, for example, from Kummer theory. Note that S is finite. The second part after this introduction is making the package. We know there is the following diagram: the local Galois group, the inertia, and the Galois group of residue field, which is isomorphic to Z hat, and it has an element 1 topological generator, and this one sends to sigma L. This one sends to sigma L, which sends x to the L. This is Frobenius element of this Galois group. And by these things, we want to make the package. For the map, GL goes to GKS, we have two cases. The first one, L not being S. Then the situation is very good in some sense. Then this map factors show GL modulo IL, which is isomorphic to Z hat. And here, so this map factors through is true. And one here goes to the Frobenius again, but here I call it phi L, not sigma L. In previous picture, I call it sigma L. Here I call it phi L in global Galois group, not in Galois group of finite field. Absolute Galois group of finite field. But again, remember that this map is well defined up to conjugation. So really, the image of one, which is phi L Frobenius, is not an element, but a conjugacy class in GKS, and it's called L-Frobenius conjugacy class. And for L in S, this is the bad case, but fortunately S is finite, so we have finite number of such things. So we have a package. Our package consists of 3 things, but many times we use just these 2 things to call it package. The Galois group GKS, the L-Frobenius conjugacy classes for L not in S, and for finite set of places L in S, we have these maps, these homomorphisms from GL to GKS. But as I said, many times we just call these 2 first things as the package. And one of the main goals of algebraic number theory is the study of not only the GKS, but also the whole package, at least the first part.
At this point, can you just summarize what actually this looks very abstract to me?
Sorry, what?
At this point, can you just summarize what you have done so far? It would help.
Yeah. So this summary of this part is really I want to make a package, and the package is this. The package is the group GKS, which was the we know that this is the Galois group of KS bar over K, and Frobenius conjugacy classes, and we want to study this package, all of the package, not only the Galois group. The point is that
so GKS is some smaller group of the absolute Galois group of K, right?
Yeah. The absolute Galois group is really very huge. For example, it does not satisfy P finiteness condition. It does not satisfy P finiteness condition. For deformation theory, really, we need P finiteness condition. But fortunately, many Galois groups that occur in arithmetic geometry are of this form. For example, any Galois representation that arises from elliptic curves or modular forms satisfy this condition. I mean, for example, let me write here with, for example, blue. For example, we know that we have a map from GQ to GL2 of ZP. This is rho E, Galois representation attached to elliptic curve. But the point is that this map really factors through some finite S.
I see.
And also this is hold for modular forms. For example, this S is the set of bad primes and also P union bad primes, P and bad primes are S. And also this is the case for modular form. The P and for modular forms, we say the level. Bad primes are primes that divide level. And we have this Galois representation. So fortunately, this is not a very bad condition, the study of this GKS, because
there's a question in chat actually. So it says that if S is the density 0 set, then what happens?
Really, I don't know. Really, I don't know.
I see.
For finite sets, it's satisfied, but for density 0, I don't know, and maybe not, because for example, for proving it, for proving that GKS satisfies the finiteness condition, you can use Kummer theory as, for example, right here, we know that form of GKS and Z mod PZ is the same as form of GKS Abelianized and Z mod PZ. And when S is finite, classical theory says us that this is finite. Kummer theory says this. When S is finite, because we have this is unramified outside a finite number of primes. But for an infinite number, I think, I'm not sure, but I think always can be infinite. At least it can be infinite. There is no necessity that be infinite, but it can be infinite. Also, if the density be 0. I'm not sure, but I think it can be infinite. Thank you. Okay. So yeah, as I said, we want to study this package.
What is role of fields?
Sorry, what?
Nothing, go ahead.
We want to study this package. A remark about this package is that when we want to study Abelianization of this package, GKS app and phi L, here phi L is not a conjugacy class. It is an element because we are in the Abelian case, and in Abelian groups, any conjugacy class consists of one element. And this package is well understood by classical theory. So we want to study this in full generality because in the Abelian case is well understood, this package. One point is that one of the reasons really that we want to study representations, Galois representations, instead of the Galois group itself, is that this package is well defined up to conjugation, and it is a difficult thing to imagine produce for some canonical construction a group which is known only up to conjugation. But there is an approach, the Tanakian approach, that try to understand not the group itself, but its representations into GLN of something. And one question is that GLN of what? But one good point is that, for example, we know that if we know the elements of G up to conjugation, but its image is a matrix, and we know that, for example, trace and determinant of matrices are unique up to conjugation. So if we change elements here by their conjugations, here the trace and determinant does not change. And it is an important fact for us. Easy fact from linear algebra, but important. As GKS is a profinite group, we would like that GLN of something be profinite too. So this suggests us to make the following definition. We call the ring A a coefficient ring if it be a complete Noetherian local ring with finite residue field Ka, which, if there is no confusion, call it K, of characteristic P. So coefficient rings are complete, Noetherian, local, with finite residue field. And as A is equal to this inverse limit, A is profinite, and the same is all for GLN. And by a coefficient ring homomorphism, I write C ring for coefficient ring. By a coefficient ring homomorphism, we mean a continuous homomorphism of local rings for which the induced homomorphism on residue field is the identity. So it should be continuous homomorphism. It should be a map of local rings. So, for example, it means that the inverse image of maximal ideal is maximal ideal, and it induces identity on residue fields. So they have the same residue in particular. And the remark is that for coefficient ring A, we have always a unique homomorphism from ZP to A, as since we assume that the characteristic of residue field K of A is P, so P is topologically nilpotent here. So always we have a map from Z to A, and since P is topologically nilpotent here, there is a map from ZP to A. And if the residue field of A be Fp, this is a coefficient ring homomorphism. And in general, we have a coefficient ring homomorphism from with vectors of Ka to A. And by with vectors of Ka is a finite field. With vectors of Ka is the unique discrete valuation ring, which is a finite extension of Zp, and it is unramified over Zp and has residue field Ka. So it is a finite extension of Zp that is unramified over Zp and has residue field K. So all coefficient rings, the category of coefficient rings with residue field K, all are WKA algebra. Now let A be a coefficient ring with residue field K, and let we have representation rho from GKS to GLN of A. We have this following commutative diagram. We have this map from A to K, so it induces this map. We have this representation rho, and this map we call it rho bar, and we name it residual representation attached to rho. But sometimes we start with rho bar itself, so there is no such a name attached to rho bar. We start with some rho bar sometimes, but no, we start with rho. Yeah. So despite the residual representation, we mean this representation to GLN. Okay. Proposition is that if rho from G to GLN of A is residually absolutely irreducible, I explained this term, and rho prime be another representation from G to GLN of A, same G, same N, same A. If trace of rho G be equal to the trace of rho prime of G for any G in G, then rho is equivalent to rho bar. Residually absolutely irreducible means what? Let I write. Residual. We have rho bar for rho. from G to GLNA, we have residual representation, residual rho bar from G to GL. What happens? Oh, sorry. Yeah. From G to GLN of K. And irreducibility means that it does not factor through some finite subgroup, but absolute irreducibility means that rho bar K bar, which is from G to GL, from G to, I write like this, GLN of
Hello. Hello. Ganesh.
Hello. Hello.
Ehsan?
do you hear me?
No,
Do
from
you?
last 2 minutes, maybe last 2 minutes, perhaps. Maybe you
Oh,
can start this proposition again.
yeah, sure. I'm sorry, I don't know what happened for my connection. Okay, I start from proposition. Let
Ehsan again happening. Hello.
do you hear me?
Yeah, sometimes you lost in your voice.
Oh, I don't know what happens.
Is it happening everyone else? Ganesh?
Yeah. Oh, there is no issue with.
Is it better now?
It is now coming.
Yeah. Okay. Oh, very bad. I'm so sorry. I don't know what happens for my connection. Let me continue, and if there is some problem, let me know, and maybe I change my
Yeah, sure.
connection.
You continue.
Okay. The proposition said that if rho from G to GLN of A is residually absolutely irreducible, and let rho prime from G to GLN of A be another representation with same G, same N, and same A, if traces of rho of G is equal to trace of rho prime of G for all G in G, then rho and rho prime are equivalent. Equivalence of rho and rho prime means that rho of G is equal to M rho prime of G, M inverse for some M in GLN of A, and absolute residually absolutely irreducible means that residual the residual representation is rho bar from G to GLN of K attached to this rho, and irreducibility means that this does not factor through some subspace subgroup of this GLN, but absolutely irreducible means that when we pass to the K bar, rho bar of K bar that goes from G to GLN of K bar be irreducible. So residually absolutely irreducible means that rho bar K bar be irreducible. And important corollary of this proposition that says something about the package that we constructed is this: let GKS, let rho and rho bar be two representations of GKS to GLN of A, and rho is residually absolutely irreducible. If for all L not in S, we have trace of rho of phi L, Frobenius at L, be equal to trace of rho prime of Frobenius at L, then rho is equivalent to rho bar. And the point is that we can also assume not only L is not in S, but we can assume that L running through a set of prime numbers outside S of Dirichlet density 1. And this is by Chebotarev. This corollary follows from previous proposition and Chebotarev density theorem. So this says something about our package, says that if we study this representation and we know something about the package, the Frobenius conjugacy classes, the trace of them, if the traces of Frobenius conjugacy classes be the same outside S, then two representations are the same. And another proposition, which is called decent, is the following: that let G from rho, let rho from G to GLN of A be residually absolutely irreducible, and let there exists some A naught subring of A, which is itself a coefficient ring, such that trace of rho of G is in A naught for all G. Then there is a representation rho naught from G to GLN of A, such that rho is equivalent to the J or rho naught, where J is the map induces by this injection from A naught to A. We have this injection. So really rho naught or J or rho naught is like this from G to GLN of A naught, and here this is GLN of A, this is J, this is rho naught, and this is rho naught of J, and we can make another map here, rho, and these two things are equivalent. And the important fact is that A naught may have a smaller residual field than A, that is maybe this injection from A naught to A may not be a coefficient ring homomorphism. Now we arrive to the main subject, deformation theory. For deformation theory, we need to define a more rigid equivalence of representations, the definition is as follows. Let we have a homomorphism of coefficient rings A1 to A0, call it F, and that we have a representation from G to GLN of A0, call it rho bar. And we have two lifts of this rho bar, rho and rho prime, be two lifts of rho bar from GLN of A0 to GLN of A1. And F here makes a map between GLN of A1 and GLN of A0, call it again F. We say that rho prime is strictly equivalent to rho, and this notion, really, this strict equivalence is relative to rho naught, is completely related to this rho naught. If rho and rho prime be equivalent and conjugation, we know that this equivalence comes by a conjugation, which means that rho of G is equal to M rho prime of G M inverse for M in GLN of A. But the conjugation given by an element not in this, but in the kernel of this map, group gamma, which is the kernel of this map. So not by all of this group, the conjugation given, but not all of this group, but by the kernel of the map of some subgroup of GLN of A1. And the most important rho naught for us is the residual representation. Here, when we take A0 to be really K, where K is equal to K of A1, I mean. This is the most important case for us. So what is deformation? We have a coefficient ring homomorphism, A goes to A0, so in particular they have the same residual field. A deformation of rho bar from G to GLN of A0 to a coefficient ring A is a strict equivalence class of liftings of rho bar to GLN of A. That is, we have a map from rings A to A0. We have a map from G to GLN of A0, and a strict equivalence class, call it rho bar, strict equivalence class of rho, so not rho, a strict equivalence class of rho to GLN of A, and such that this is, if we call this F, this is also F. This is called a deformation. So this is called a deformation, this lifting called deformation of rho bar to GLN of A. And as I said, most important case is the case where A0 is equal to K of A real. One of main theorems is the following. Let rho bar from G to GLN of K be some representation such that satisfies two conditions. First, G satisfies P finiteness condition. And second, rho bar is absolutely irreducible. Then there is a coefficient ring, which we call it R univ, R universal, which is really just dependent to rho bar. And a deformation from G to GLN of R univ, which we call it rho universal. A deformation rho universal of rho bar, which get with this diagram, to R univ, which is universal in the sense that given any deformation rho of rho bar to any coefficient ring A with residue field K, note that R universal also has residue field K. So given any deformation rho of rho bar to any coefficient ring A, rho is obtained from rho universal by a unique homomorphism of coefficient rings from rho univ to A. I mean, we have this, really, I can write another map. We have this map to GLN of little k, and this commutative diagram, the following diagram, G goes to GLN, really makes the deformation of, this is rho bar, and this rho makes the deformation of rho bar to A. And any such deformation comes from a unique deformation to GLN of R universal by a map from R universal to A. If we call it F, then the induced map on GLNs also we call it F, and really rho is nothing other than F or rho universal. So any deformation comes from rho universal by such a map, by composition with such homomorphism that comes from the ring homomorphism R universal to A. In other words, the following functor is representable by R universal. What functor? Let d rho bar be a functor from coefficient rings with residue field K to set. And I write here Artinian because I want to say that in application, we can restrict ourselves to Artinian coefficient ring with residue field K. And instead of representability, we think about a notion called pro-representability that I have no enough time to discuss about it, but not very important. You can see discussions of it in the references that I will say at the end of talk. Okay, the rho is from coefficient rings with residue field K to set and satisfy two conditions that is covariant and the rho of little k is a single element, such that since any coefficient ring with residue field K like A to the set of strict equivalence classes of deformations of rho bar to A. And representability of this functor, in other words, this functor is representable. This means that the rho bar of A is just hom of R univ to A, which is this hom is hom of WK algebras, ring of width vectors over K, and hom of coefficient rings.
What is this algebra?
Sorry, what?
What is this algebra, WK?
WK is the ring of width vectors. As I width vectors, I explained it before.
Okay,
W.
okay.
WK with vectors over K. It is really, as K is a finite field, WK is the unique unramified extension of ZP, which has residue field K. Unique unramified extension of ZP with residue field K. So, let us say one remark. The study of this functor d rho is called the deformation problem for rho bar, and the following theorem, the above theorem says that the deformation problem for rho bar is representable, and this is a great theorem due to Barry Maser.
Which one?
Barry Maser.
Which theorem? This is representable, that's right.
This theorem, the representability. If rho bar is such that if G is satisfy P finiteness condition and rho bar be absolutely irreducible, then there is such universal deformation. This is called universal deformation. And this ring are called universal deformation ring. And existence of these things, and in other words, representability of this functor d rho by R universal is the theorem of Barry Maser.
Which paper of him? Which paper?
A paper called, really a paper that deformation theory introduced, goes to 1985, called something like Deforming Galois Representation or something like that. It is in a book that called Galois Groups over Q, edited by Galois Groups over Q. This is a book that contains some nice articles, research articles, edited by Ribet and some others, maybe Ihara, Sir Ihara. And Maser in this book has a paper introduced first time the deformation theory of Galois representations and proved the representability using Schlesinger criterion. But after Maser, some other people proved the representability using other methods. For example, Lenstra and Joe Smith proved the representability by, in some sense, an explicit construction, and Faltings, I think, prove it by another method. So this important theorem says that the deformation problem for rho bar, when rho bar is absolutely irreducible and our group satisfies P finiteness condition, is representable. And note that we had deformation. This is called the universal deformation ring, and rho univ called universal deformation, and a spec of R univ is called the universal deformation space. It is an affine scheme, and some people study this deformation theory in terms of algebraic geometry. Okay, next topic is a Zariski tangent space, but it seems that I have no enough time to say many things about it, so I just can. Okay.
Want to stop or you want to go? Maybe 10 minutes you can take if you want.
Oh, thank you. I want to speak about this one page.
Okay.
Okay. The earmark of representability is that if you have a diagram A, let me erase and write again. This is better. If we have a diagram like this, two maps from A and B goes to C, call it alpha and beta, and let all of these things are coefficient rings. We can complete this diamond by fiber product, and let D also be a functor from these rings to sets, set valued functor. We know that from D of D is covariant functor. So from D of A times B over C, there is a map to D of A, and there is a map to D of B. And by the universal property of product, we know that there is a map from these to the this fiber product. So we can construct this map, we call it H. And earmark of representability is that D is representable. If D be representable, then H is a bijection of sets for all diagrams, for all such diagrams. And also the vice versa is true in some restrictions. If, for example, we assume that these coefficient rings are Artinian, as I said before, that we can restrict ourselves to Artinian, then the vice versa is also true. But in some sense, this theorem, if I remember truly, this is a theorem due to this theorem. This is really a theorem due to maybe Grothendieck. But in some sense, it is useless in practice because it is very hard to check the bijectivity of H for all diagrams. And yeah, so
what do you mean by all diagrams?
All diagrams in this manner. For a category, you have all such diagrams. I mean, I call this a diagram.
Okay, such diagram for the coefficient ring with certain conditions.
Yeah. Really, it is very hard to, for example, if we restrict ourselves to the Artinian case, that the vice versa be true, it is really very hard to check the bijectivity of H for all such diagrams that we can complete it by fiber product. And then if we can check bijectivity for all diagrams, then we get that D is representable, but it is very hard, and it is in practice really useless because we cannot check all diagrams really. But Schlesinger criterion that we will see maybe next week says that it is enough to check very few diagrams to get the representability. And it is related to Zariski tangent space. I at the first introduced Zariski tangent space, and after that we have Schlesinger criterion that remains for maybe next week, or maybe if I can say today. Zariski tangent space of a ring of a of any ring, especially of a coefficient ring, defines as TR is the Zariski tangent space, is nothing other than K vector space homomorphisms from R, the maximal ideal of R, over P and the ideal generated by P and MR square and K. P, remember that P is the characteristic of residue field of R. This K vector space is called the Zariski tangent space of a ring R, and we want to say this in terms of functors. Let us introduce another notation. Let K epsilon such that epsilon square be 0, be the ring of dual numbers over K. We call it ring of dual numbers, and it is K plus epsilon K, as epsilon square is 0, such that epsilon K is the ideal of this ring K epsilon of a square 0. Then theorem is that TR, that as we said, this is equal to this harm, really is isomorphic to this harm, homomorphism of coefficient rings from R to K epsilon, and fortunately it is dr of K epsilon. By dr we mean as we work from with functors from coefficient rings with residue field K to sets always, dr, all these are distinct, and by dr we mean the functor represented by R. So it is of the form ham R of and something. So this dr is the functor ham R. So the Zariski tangent space of R is really dr of K epsilon. This is very good. Can I continue for maybe 5 or 10 minutes?
Take maybe 5 minutes.
Oh, thank you. This isomorphism that Zariski tangential space is the dr of K epsilon suggests that we can make the following definition for any functor D not necessarily representable. We define the Zariski tangential space of D as TD be the TD, by TD we mean the Zariski tangential space of D, as the D of K epsilon. And note that until now, TD, which is D of K epsilon, is just a set, and we want to make it a K vector space. Just I want to say about Shahoseini. Yeah, so maybe it's 5 minutes enough for me. Again, remember that we have this diagram A, B over C, that both goes to C, and we can construct a fiber product. And also we have this map H from D of A times B over C goes to D of A times D of B over D of C. Shahoseini criterion has 4 conditions. H1 is that let this H is surjective if the map alpha from A to C is surjective. H2 says that H is bijective if the map from A to C is really K epsilon goes to K. So A is K epsilon, C is K. H3 says that TD, which is the D of K epsilon, is finite. Is a finite set. Our Zariski tangent space for D is a finite set. And H4 is another thing that needs more things to say, and I skip it. And Shahoseini theorem says that if this satisfies H1 to H4, then D is representable. The vice versa is trivial, because if it be representable, then all diagrams by Grothendieck theorem, all diagrams, H is H really, if D is representable, H is bijection for all diagrams, and especially for that 4 diagrams that appear in Shahoseini criterion. But Shahoseini criterion says that if we check just these 4 type of diagrams, then we can say that D is representable. And yeah, I can skip here.
So D representable means that the vector space, the set that you attach, is TD, is vector space.
Sorry, what?
So D being representable under this Linger criteria, it implies that TD is the vector space, tangent space.
Yeah. After this, I want to make really, I have no time. This for making the Zariski tangent space that no is just a set. To make it really a K vector space, we use some other definitions, near representability and something else.
Okay, maybe we can postpone it for next time.
Yeah.
But I would like you to summarize maybe once what you did today. It would be helpful next time.
Yeah, sure. So I go to the first page. We see that we have some notation. This is important. Max K bar S is maximal algebraic extension of K in K bar, which is unramified outside S. And its Galois group is GKS, Galois group of K S bar over K, which is profinite group. We see that this map is not an actual map, and it is just well defined up to conjugation. So so we need to think about it more better than an exact map. So we need to check real representation. Note that GL, local Galois groups, are topologically finitely generated, and GK, global Galois group, is topologically countably infinitely generated. A weaker condition than finite generation is p-finiteness condition that is defined when for a profinite group G, we say that it satisfies p-finiteness condition if for all open subgroups G naught of finite index of G, the set of continuous homomorphisms from G naught to Z mod Z be finite. GL is satisfied this p-finiteness condition because it is topologically finitely generated, and GKS also satisfies for a finite by Kumar theory, but the global Galois group, the global absolute Galois group, does not satisfy p-finiteness condition. We made a package that was the GKS, the Frobenius conjugacy classes for L not in S, And we can also think about this finite set of maps as some object in our package, or we can ignore them, not important really. And one goal of algebraic number theory is the study of this package. And fortunately, many of representations, especially that comes from elliptic curves and modular forms, are of really factors through groups of this form GKS for a finite S. So a study of these groups is not very restrictive. And we know this package in the abelianized case by classical theory as this group, as this package, these Frobenius conjugacy classes are just well defined up to conjugation. It's better to think about them in terms of matrices, because invariant of matrices, trace and determinant remains the same when we change our elements up to conjugation. So Panakian approach suggests that think about group, think about not the group itself, but also its representations. And we study representations of G into a GLN of something that be profinite. So we make the following definition that A is called a coefficient ring if it be complete Noetherian local ring with finite residual field K and of characteristic P. Examples are, for example, ZP, or for example, power series over ZP with finitely many variables are coefficient rings. And these coefficient rings and matrices over them are profinite. And homomorphism of coefficient rings are really respect to topology, respect to local nature of rings, and respect to residue fields. And this is the algebra structure of coefficient rings that we have. All of them have ZP structure, and if they have residue field Ka, they have WKA algebra structure. The residual representation, if we have a representation rho from GKS to GLN of A, the residual representation is the representation that comes from this composition. We call it rho bar from GKS to GLN of K bar. And the point is that if we know our package, if we have two representations of GKS such that the trace of Frobenius be the same and one of the representations be residually absolutely irreducible, then the two representations are the same up to conjugation, are equivalent. And we had a decent argument. Okay, deformation theory. For a map of coefficient rings A1 goes to A0, deformation of this representation from G to GLN of A0, rho naught, the deformation of rho naught. Oh, sorry. At the first, I should define a strict equivalence. Let we have a representation from G to GLN of A0, call it rho naught, and let we have two lift of it, rho and rho prime, to GLN of A. We say that rho prime is strict equivalent to rho relative to rho naught if these two representations, rho and rho prime, be equivalent, but not by elements of GLN A, but also by the elements of kernel of GLN of A to GLN of A naught, kernel of this map. They be conjugate by an element of that kernel. And most important case for us is the case where A naught is really the little k, the residue field of A1. But what is a deformation? By deformation, we mean we have a coefficient ring homomorphism from A to A naught, and a deformation of rho bar from G to GLN of A naught to coefficient ring A is a strict equivalence class of liftings of rho bar to GLN of A. This diagram, we have this representation, and a strict equivalence class of this lift is called a deformation. And again, most important case is the case where A naught is equal to little k. And Mazur's theorem says that if rho bar from G to GLN of K be some representation that satisfies p-finiteness condition and rho bar be absolutely irreducible, then there is universal deformation ring, a universal deformation ring, and a universal deformation, that all other deformations come from this one by a ring homomorphism. I mean, if we have any deformation of rho, any deformation rho of rho bar to any commutative ring A, then rho obtained from rho unique by a unique ring homomorphism from rho R universal to A. That is, we have this following diagram. If we have this, we have this map, the residual representation to GLN of K. If we have a deformation rho from G to GLN of A, and also we have this universal deformation rho unique, then rho is nothing other than F or rho unique, that F is this map. The induced map from R unique to A, which on GL, the induced on GLNs, that I call it again F. In the terms of functors, the Mazur theorem says that the following functor is representable by rho unique. This functor that is called the deformation problem for rho bar from coefficient rings with residue field K to set, that sends any coefficient ring to the set of strict equivalence classes of deformations of rho bar to A. And Mazur's theorem says that the rho bar of A is nothing other than homomorphisms from R unique to A. And yeah, we had this earmark of representability, that we have this bijection if and only if this D is representable, but it is hard to check these bijections. This is a useless theorem. We had this notion of Zariski tangent space, a notion from commutative algebra. TR is defined as homomorphism from this K vector space to K, MR over P and MR squared, where P is the characteristic of residue field of R. And we try to say this in terms of functors. We introduced the ring of dual numbers, K epsilon, which is K plus epsilon K, and TR is nothing other than homomorphisms from R to K epsilon, that is dr of K epsilon. dr was the functor represented by R. dr is nothing than R. And this suggests that for any functor not necessarily representable, define TD Zariski tangent space to be D of K epsilon, which is really, which we want to be a K vector space, but just know is a set next week we make a k-vector space structure for it. Before making this k-vector space structure, we had Schlesinger criterion, we had these diagrams, and we have this map H. And Schlesinger criterion says that if we have these 4 conditions, then if we satisfy these 4 conditions, it is representable. So we need to check the property of H, for example, bijectivity or surjectivity or finiteness of the set of Zariski tangential space and something like that to deduce that these representable. This is a great theorem due to Schlesinger, which is very helpful. And yeah, that was all of what I said.
Thanks, Ehsan. It was very wonderful. Actually, I'm looking it our first time, but still it makes sense something.
Thank you.
So
And sorry.
really... No, it was very wonderful. I'm saying that.
Thank you. Thank you. Sorry for problems in my connection. I'm sorry for speaking maybe fast because
No. It was very good, and actually we are looking for first time. So for me, it was good actually.
Thank you very much.
Thanks. See you next week. Ganesh, can you stop the recording?